All right, good morning, everyone. Let's get started with today's exercise. We're going to be doing a lot today in just 50 minutes. So I want us to be as efficient as possible. So I did share with you all through GitHub two data folders with many images in each one of them and one complete script. So I do assume that you all were able to download the 2017 data, so I did not share that with you. I did share with you the data for 2019 and 2020, which thanks Clint. So Clint was able to download data for all 3 years. I was not. I know some of you were not as well. So if that was the case, then I shared those images with you. You would basically obtain those images using the same script that we pulled the data from 2017. It's just that we ran into the issue of getting to the limit of our free quota through Planet. So if you just wait for your quota to reset, which it does every month, you would be able to then download those images if you want. Of course, this is not really useful if you need a lot of imagery right away, right? But if you plan ahead and you know you're going to need a lot of imagery from the past, from their archive, you can plan ahead and spread out your downloading needs over time a little bit better. So I share with you those two folders with the data. I asked you to get those folders from our GitHub repo and move them inside of the code folder of this project. I am assuming y'all did that. So that solves one of the issues as far as not being able to download all the data. And then the other issue is after the last class, I went back to my office and I was looking into the script. I was looking into the images, trying to understand why we were not getting some of the numbers that I was expecting. So for example, when we were doing the geometry backup, instead of getting about 46,000 data points, which is the number of pixels in that image, we're getting like 120,000. In class, we didn't have the time to troubleshoot and understand why that was happening. I went back and I looked again at the code, looked again at the data, and I was able to identify that. So I developed a better script that identified the issue and addressed the issue. And I shared that script with you as a complete script, also through GitHub. It was on the 05 complete code folder. I asked you to move that script into your code folder of this project. So the code is in the 05 folder. It's not in the 04 class code. It's 05. I think there's only a couple in there. So it's the one that has the name for this exercise. It's like 04, 22, imagery processing, 2017 complete. That's the one. So I'm giving you the whole code. You're not going to have to change anything, at least not in this script, but I do want to walk you through what I identified as issues, how I address it, so you understand what happened behind the scenes. And then we're going to go through this script so you get the processing on your side, and then we're going to repeat this script for the other 2 years. So in the end, you have a median value for each one of the 3 years. Also, what I noticed is when I did the median of the 2017, which we had done, but I did again doing the correct steps that I was missing in the first time around, I got a slightly different median map and a better median map, and we're going to talk about it when we get there. All right. So I'm going to start going through this script here. Again, you don't have to code anything. You may just have to adjust perhaps some of the paths or some of the naming convention, but the actual code is all there. So let's start running this. So just running the packages first. Go ahead and import the boundary. So we did this first steps here of just importing one image. So this is again one image from 2017. It was the first one. We did a little bit of processing where, if you remember, on this single image, the single stars object called image, we don't have the bands as dimensions. So in this first panel here, it shows us the dimensions, which are actually the things that we can work with. So if I want to like calculate a vegetation index, I need to have those bands as dimensions. They're not as dimensions, they're here as, I don't remember how these are called. What is the name that stars give it? But they're under, all the bands are under this row right here. We want to pull them out into the dimensions part of the stars object. So we use the split for that. Then once we do the split, those bands become available as dimensions. Then we can use them to calculate Green DVI and only keep Green DVI after that. So if you run this, you have this dimension now that is Green DVI. From that, we use map field to explore it. I'm not going to do that again. Then we determine a list with all the files. So let's go ahead and create this list again, because that's going to help us to read all those 47 images for 2017. So if we ask for the length of the list, we see there are 47 images in that list. And the first one of them here is the path and the name of that file. We talked about the file having some metadata in the file name. So originally, we only explored the metadata of the date, the acquisition date. In the chunk below, one of the things I changed is I also extracted the acquisition time. So this 15:30:46 is 3 p.m., 30 minutes, 46 seconds. So that was the time of the day when the satellite went over this field and acquired this image. We're going to be using this for the processing as well, and you're going to understand why in a couple seconds here. All right, just skipping all that. This code here, for the most part, is the same. One difference that you're going to see is, again, I am extracting the time from that metadata, just using that string sub that we used previously for the S date. I guess something to call your attention here is, if you recall from the previous exercise, the separator of // worked if you are working in a Mac. If you are working in a PC, I believe you were using, let's see the full name here. I think you were using 273.1/ as your separator. So make sure you have that change on your side if you're using a Windows machine. So again, the one difference from the previous exercise is I am extracting the date as before, but also the time. So we're using the map functions here to read all those stars objects. And then we are doing that processing of splitting the bands, calculating Green DVI, selecting Green DVI only. We were doing this before. I am adding something new here that we did not have before, which is a column that gives me an image ID, which is going to go from 1 to 47 in my case. That is just to help me to identify which images I want to plot side by side. It's nothing more than that. So a few differences in this code is I am also pulling the time, and I am creating a new column called image ID. We did not have this before. Make sure you go ahead and run this chunk. We're going to explore this a little bit. So if you just print this object right below, now you have an image ID column that goes from 1 to 47. We have the dates, we have the time, and we have that image W, which is that stars object that we had before. All right, so one thing, this is going to be a difference from the previous time, so I want you to follow me here especially. One thing that I did not realize is that I thought I had checked the imagery data, and for some reason I thought we did not have any date duplicates, meaning we only have one image for a given day. And that was, I don't know what happened on my side, but that was not actually what happened. So we have many days that have more than one image. In some cases, I think up to 4 images per day on this, for this field. And that's one of the reasons why we're getting some problems when we were doing the geometry. So whenever if you think of it, if you have more than one image per day and you're doing the processing as we were doing, the algorithm is basically not sure how to accommodate more than one image per day, because that was not part of our code. So what I did in this code here was to identify those days that had more than one image, and then inspect what was going on there, and then select only one of those images to move forward. So that's what this is going to be doing. And just to give you some background, different planet constellations have different number of satellites. I believe this number may not be very accurate, but just to give you some idea, I believe that the constellation we're using has about 170 satellites, which is a big difference from Sentinel, which is another source of imagery. Sentinel has 2 satellites. Sentinel-2 at least has 2 satellites. This constellation that we're using from Planet has over 100 satellites. So the likelihood of more than one of those satellites flying over your field the same day is high, and you have access to all that imagery. So that's why we're getting so many duplicates, because there's a lot of satellites flying around collecting data. So what I did here in this code is I'm starting with all those images. I'm grouping by date. I'm asking for a tally. So this is basically going to tell me how many images I have for each date, and then just filtering whenever the number of images is more than 1, just so we can explore the extent of how many of our dates have more than 1 image. So here we see that we have 13 dates that have more than 1 image. Some of them have 2, some of them have 3. I think in this year, 3 is the max, but in I think 2019, which we're going to be doing next, has some days have even 4 images. So then my question was, okay, why do we have so many images? Are they all of equal quality? Should we take the average of those images, or are they of different quality and we should only keep the good ones and not try to average things, because we're going to be adding noise that way? So initially, here's what I wanted to do. The rules that I decided to use to determine what I was going to do next was, in the same day, if I have more than 1 image, I want to check how many NAs there is in those images. If they have the same number of NAs, especially if that number is low, it means they are comparable. However, what I noticed, and you're going to see that in a second here, is that for many of these images, we were actually getting 1 image very good, like with most of the data. The other one, it was like 90% of the image was NAs. So it's very easy to decide you want to keep going with the one that has most of the data. So I wanted to use this rule of keeping the one that has the least NAs. And if I have 2 images on the same day where both of them have an equal number of NAs, so I cannot differentiate them by that, then I would select the one that is closest to solar noon. So the closest to solar noon, the least effect of solar angle you're going to have on the image. So that's why we're extracting the time, because now if they have on the same day, 2 or more images have the same number of NAs, then we're going to use the acquisition time as the rule. So whichever one is the closest to solar noon, that's the one we're going to keep going. All right, so I left you here this code, which I'm basically just starting with all images. I'm creating this column here called sum for summary, where for each image, I'm transforming to a data frame and then summarizing, getting the total number of observations, then getting the number of NAs, and then getting the percentage of NAs in that image. So I can use this rule here to determine which ones I'm keeping, which ones I'm leaving behind. So if you just run this code here and print that, so here's what we have: image ID, the date, the time of acquisition, we have the image, and now we have these columns here. Uppercase N is the total number of observations. As you see, this number is the same for every image. If you remember raster files, even if they have NA cells, that cell is still there, right? You're still going to have every single cell within that bounding box. So that's why our uppercase N number of observations is the same for all of them. Now, NA column is how many of those total N cells were NA or not available, no data. And then I just took the ratio of these and multiply by 100 to get the NA percent. So here, the first image has 4% NAs, the next one has 23, and so on. So I want to show you here, for example. So 0507, you can see here, this is image ID 3 and 4. They have a very similar percent of NAs, but we could still select the one that has the fewer NAs in this case. So a few things that I noticed, right? So normally date duplicates have different percent of NAs. So image ID 3 and 4 is one example of that. When the duplicates have the same number of NAs, so in the case of image ID 11 and 12, I was keeping then the one that was closest to solar noon. So image ID 11 and 12, let me see if on my side I can squeeze things to enough to be able to see. Yeah. Okay, so image ID 11 and 12, they're both from June 26. They have the exact same percent of NAs. So I was using the acquisition time. Whichever one was lowest acquisition time, which means closest to solar noon, that's the one I was keeping. And also some of these images did not really have duplicates, but they had a large percent of NAs. For example, image ID 25, if we check on that. Well, I guess image ID 25, actually, we do have two dates. And one of them had like 80% NA. So we were removing that, but I think there was another one, maybe 33. Let's see, 33. Yeah, so notice how 23 is not a duplicate, it's only one image for August 22nd, but it's 96% missing data. There's really not a good reason to keep that. Yeah.
Is it possible that you have only one image for a date, but I have two images for the same date?
Okay, so Ujwal is asking, is it possible that I have just one and on your side you have two? It is, I guess. I mean, at least with the 2017 data, it is, because I know some of you were getting 48 images, I was getting 47. So maybe that discrepancy is there. And I'm not sure why, because the only difference is our boundaries are slightly different. But still, I wouldn't expect that small of a difference would create different images being pulled, but I guess it did. Yeah, so this is how I was identifying the percent of NAs for the images, and then I inspected each pair that had more than one image per day to understand what was going on. I found the patterns of normally when you have duplicates, one of them has a lot more NAs than the other, most of the time. In some cases where that's not what was going on, so if they have a duplicate and they have the same amount of NAs in a day, then I was only keeping the one that was closest to solar noon, as that would have less effect of solar angle on the quality of the data. All right, so I just want to show here one example of image 3 and 4, image ID 3 and 4, which were the ones, let me show you here again. So May 7th, both images from May 7th, where one had 4% NA, the other one had 6. So this was very close. So if you just run that chunk, oh, sorry, it's not called test. I was making the test, and that's why it was still with the name. So this would be, so we can just replace test with all images dup, which is what we had above. And I think this should work. All right, so these are, again, two images from the same date. If I just turn one of them on and off, let me try to zoom out so you can see. So really the difference here between these two is that image 4 has that top corner missing, whereas image 3 does not. So this is a very small difference in what is missing. So just image 3 has that top corner missing, image 4 does not. And again, they're from the same date, so I would keep the one with the least NAs. In this case, it's a very small difference, but in some of them, you have 4% NA in one of the images and then like 50% NAs in the other. So it's a lot more discrepant in that sense. And another example here in my site, image IDs 11 and 12. Again, you need to replace the test here with all images dup. If you run this chunk, you're going to see the case of the closest to noon, where they have the same number of NAs, which is a very low number. But one of them, so if you turn one of them off and then the other on, you're going to see that they're both very complete. And so in that case, I would select the one that is closest to solar noon. So I did that in an automated way. So you could come here and look for each pair and then only say, well, keep this one or filter that one out and so on. I did that more automated. So I came here to the all images up, group by date, and then first thing I kept, so within a date, if the date had more than one image, I was filtering the one that had the minimum NA. And after applying that filter, if there was still duplicates, then I would apply the next filter, which is with the minimum time, which is the acquisition time. Minimum time in this case going to mean closest to solar noon. That's why I wanted to keep. Then I also have this last filter, just because one of the images had more than one of the images was not a duplicate, but it had like 90% NAs. So I wanted to remove that one as well. So if we just run this chunk, you're gonna notice that we in the end, we have 29 images moving forward, where before we had 47. So we already removed a lot of duplicates that based on NA and then time of acquisition, and also if they had too many NAs, even if they did not have a duplicate, I'm taking them out. So if you go through the date now here, you're gonna see that we don't have duplicates anymore.
Where did you take out the ones that we just took in on that view? Where did those come out? By images group or what part of the page?
You mean on the map view code?
No, like on the, did you take that out on the all images? So on that, like, you know, we had to decide which one is all.
So what I did here is I used this all images duplicate to create the summary of the NA percent, right? So this all images duplicate still has the stars objects under image W, but now it has these columns here, including the percent of NAs that I can use for the decision making. So on this chunk here is where I'm keeping. So I'm grouping by date. So if a date has more than one image, right? Yeah, this is where the filter is being applied. Awesome. So then I crop to the field. This is same code. There's nothing new there. We're cropping to the field, if you remember. This may take just a quick moment here. You don't have to print anything else in that chunk. We can just keep moving. And then I extracted the pixels. So this is the same code as before. There's nothing new here. I'm just extracting a pixel level data by transforming this to SF, if you remember that. So you can go ahead and run that. Now the difference is before we were doing this to 47 images with a lot of duplicates. Now we're doing to 29 images without any duplicates. So now on the pixels, we have like about 1,300,000 rows. And if we just do a group by date and get a tally to see how many pixels we have per date, this number here should be the same across. While this is going through, I just want to tell you, I want to advise you again to not run the plot chunk that comes right after it in class, as that's gonna take some time to go through. So I don't want you to get stuck there. But after class, if you want to run it, so we have that map with like all of the 29 images that I showed you in class, then you're welcome to do that on your side. This is taking a little longer than what I expected, at least on my side here. But I just want to, as this is still running, I just want to keep forward and tell you, so do not run this, do not run the DigiSave. This piece of the code here we already had before, which was just getting the pixels, dropping an A, only filtering some of the pixel IDs and plotting them on the date on the x-axis, gradient DVI on the y-axis, and looking for that pattern over the growing season. Let me see, this has not run yet. Is this still running on your sides? Okay. I just want to wait another minute here, and if it doesn't go through, I'll cancel it so we can keep moving. Okay, we finished on mine at least. So here you see that for almost except for one of the images that had an ace, that still had an ace, a little bit of an ace, and it was not a duplicate, we have 44,930 pixels on my side, at least. Yours may be a little bit different because of the boundary difference. But bottom line is they're almost all with the same number of pixels per day. And in this part here, we were getting different number of pixels before. Because before, we had all the duplicates in there without realizing. So when it was grouping per date, if you had two images, you had here, almost like 90,000 pixels. So before, this was one of these discrepancies that in class, I saw it and I was thinking, well, this doesn't seem right. Let me troubleshoot it later. So now they're very similar. The maximum is 44,000 as it is the maximum number of pixels. We're not going over the maximum. In one of the images, we go a little bit lower. If you were to plot this image, you would see that this has, I think, 6% NAs, whereas everything else has only 4%, which is actually just around the bounding box that you get those 4%. All right, so if you, again, don't skip this, do not run or skip this one and this one, because those take some time to run. But you can come to the next one and run this. So the pixels drop an A, we're filtering just some pixels and plotting them. This is what we see. I left you the code here that we can actually see the exact date on the x-axis. So although it may be a little bit difficult to see, but this one that comes very low, one image that drops a lot on gradient DVI is July 6th. So that is one of the images that when we were looking, it seemed like there were some clouds. If we were to look at the plot that comes from this chunk, which again, we're not running, but when you run that, you're going to see that is the image that seems like have some clouds. So I do want to remove this image from this data set before getting the median of the pixels. So that's what I do on this next chunk here. If you get the number of rows now of your pixels F, it should be slightly less than your pixels, right? Because you removed one date, you remove 44,000 pixels or rows from pixels F. All right, then we talked about here, you can just go ahead and run this whole chunk, which is just showing what we're doing on the algorithm. So this is just the gradient DVI response for one of the pixels, and we're getting the median of the y-axis, the median of the gradient DVI over the growing season, which is this red line for this one pixel. Now, the algorithm on the chunk next is going to do this for all the pixels over time. So remember, we're taking all those dates for each one of the pixels, creating this time series and getting the median. So in the end, each pixel is going to have just one value, which is the median of that pixel over the growing season. And instead of having 29 images, we're basically summarizing all that into one image, right? Which is going to be the median of the growing season. So I did create a geometry backup now because so one thing to pay attention here is because now all the images or almost all the images have the same number of pixels, which is what it should have been, and it was not last time because of the duplicates. But because now they do have all the same number of pixels, you just need to make sure you pull one date where you don't have an ace. So if you come back to this tally here that we did before, that first date that I'm pulling, that I'm using as my template for the geometry backup has the 44,930. I will not want to use 0425 as my geometry backup because that has some NAs. But if I use any of the other images as my geometry backup, it would work. So I just wanted to point this out as you're looking on your side. All right, so going back to the geometry backup, I'm just pulling the geometry from this date as my backup. Then to calculate the median, I am dropping the geometry because again, if you keep the geometry there, this takes a long time. The fact that it is an SF object with a geometry for each one of the pixels makes this process take long. So if you drop geometry, this runs in 2 seconds. If you do not drop geometry, it may take 10, 15 minutes. So that's why we're dropping geometry and then bringing back with the backup, which is we're doing all throughout this code. So dropping geometry, dropping NAs, grouping by pix ID. So remember, if you group by pix ID, then you're being able to calculate for each pixel the median of the growing season. So then we're doing that with a summarize. After we do that extraction of the median, we bring back the geometry with the geometry backup and then transform that to SF. So if we go ahead and run it, and then we can make a plot of it. So this plot does not take long. You can go ahead and run it. This is how it looks like. So if you remember from last time, we saw some streaks, right? And I thought it was because just like the way that's displaying, but it was in fact an artifact of having too many duplicates in the same day. It was creating that. So now we don't see those streaks anymore that we're seeing. And this is the median gradient DVI for this field. You can save that on the ggSave if you have not done that yet. And then we can compare that with our actual yield monitor data, clean interpolated from this field. And again, our imagery is finer resolution than our yield monitor data. But overall, I think we can see some of the similar patterns as far as seeing so on the yield, we don't see as clearly, but on the imagery, we do see that those gullies are very clearly lower gradient DVIs, which you would expect. We have a higher gradient DVIs on the south side here, which you can see here. On the yield, we don't see such a strong effect on this, I guess, northwest side as we see on the yield. But we also see this portion here being lower yielding and also lower gradient DVI on this field. So something to keep in mind, this crop was cotton. Cotton, perhaps of the crops that we work with, the row crops we work with, is perhaps the one crop where higher greenness or vigor does not always translate to higher yields. Because again, cotton is a perennial crop that we annualize, which means that if you give it too much nitrogen, too much water, it's gonna try to become a tree and not give you a lot of bulbs. So there is a balance between how much we want it to grow vegetatively and how much yield it's gonna give you. That is, at least with the crops that we grow, is very specific to cotton, right? So corn, soybeans, peanuts, other row crops that we grow in Georgia, normally the more vigorous the crop looks like, the more yield you get in the end. And again, this crop we're looking at here is cotton. So that relationship between how vigorous the crop was in the season and how much yield you get is not as closely related as if this was a different crop. So I wouldn't really expect these to map. If this was corn, I would expect for this relationship to be closer. This is cotton. So, again, there is that caveat there. But we can really see that, let's say if you're working with a grower that does not have yield monitor data, or maybe a crop that doesn't even have a yield monitor data or yield monitor for that crop, you can still get a pretty good sense of spatial variability of yield potential, right? So notice that the map we have here with the median gradient DVI is still gradient DVI, it's not yield, right? But we can get an idea of the different potential of yield in this field by using a vegetation index from satellite like this. So that was my goal, was to show you if you're working with a grower that, does not have yield monitor on their combine or their picker, or maybe with a crop that doesn't even have yield monitor developed yet, you can still use in-season imagery to get some idea of areas of the field that are higher yielding and lower yielding through this. All right, and then if you want to go ahead and export again, because now this is the actual correct layer that we wanted to extract, please run that chunk, save your script. You can close this script here, clean your environment, because we're going to repeat this process for the next 2 years. What I want to ask you to do is, so if you can look on my screen right now, I just want to show you a way. I don't know if you already found this out, but If I just navigate on my files in our studio, it's harder to copy and paste things. What I do if I want to do that is I click on that engine and I click on show folder in new window. That's going to basically open that folder on your, file system in your computer. So what I want to ask you to do is go in code, copy that imagery processing 2017 completed that I share with you that we just finished, paste that, and then rename it to, instead of being 2017, rename it to be 2019. So we're going to edit this code that I sent you for the 2019 data. That again is, I send the images to you through GitHub for that year. All right, I'm going to launch here on my side at 2019. There's going to be some differences here. I have already developed the code on my side, but I want you to make the changes on your side. So again, copy that 2017 completed imagery processing, paste it, rename it to 2019 instead of 2017, and then launch that that script on your R Studio. Make sure you clean your environment here. So we start fresh. You can do that by clicking on that broom icon to clean your environment. Okay, so the goal here, let me just give you the vision so you understand where we're going with this. My goal is to have a one median map and data set for each one of the years. Okay, so we did that for 2017 already. Let's start doing that for 2019 at this point. You don't have to rerun the packages. You will have to rerun the boundary. So here is a difference. I have already, oh, you know what? I guess we can just skip the image because this was just for us to understand what was going on. We don't really use this moving forward. So just skip this chunk for sake of time. You don't have to run the image W either. That was just for us to understand what a single image is doing. Really, the first thing you have to change is coming to the RAST list chunk. Right now, the path that you have is the path for the 2017 folder. What I want you to do is you can delete this path and then navigate to that 2019 folder. So // hit tab, go in data, hit tab again. You're going to select the class cotton, PSC, and ortho, 2019, right? The 2019 is the one we're going to work with now. The pattern is still the same, so we don't have to change the pattern. Just make sure you run the RAST list, pulling the imagery from the 2019 folder. If we take a look at the length of the RAST list, there's 130 images for 2019. So even more than what we had for 2017. There's going to be a lot of duplicates here. You can skip everything. I think I left you all the code here. There's no change. So you can just run the all images W. It should work fine. You can skip printing things here just for sake of time. You can skip the map view as well. So on the duplicates here, I do want you to run this chunk so we inspect how many duplicates we had. So notice that for 36 days, we had at least 2 or more images. In some of those, we have 3 images. Some of them we have 4 images. So notice here how in 2019-07-04, we had 4 images in a single day. Right, so we're going to have to address all these duplicates. You can go ahead and run the all images duplicate. This should still be the same code. It's just going to create that summary for us with the NA percent and the time as well. So we're going to use the same 2 rules. If we have a duplicate, we're going to first filter by keeping the one with least NAs. And if you still have duplicates, we're going to filter the one closest to solar noon. You don't have to run any of these map views. That was just for us to inspect. You can just go ahead and run the all images F. So we filter that. Again, the same rules that we had before. If you print it, you're gonna see that we have 77 images now. So almost half of what we had originally after removing the duplicates. So after that, we're just cropping again to the field. So run the all images underscore crop. That's still the same code. You don't have to print after it runs, just so we, again, for sake of time, but we do want to crop it. So it is taking a moment here to go through. All right, it went through on my side. Now we do want to extract the pixels just like before. You can go ahead and run that code. It may take a moment. It went from my side, so I'm going to keep moving. You don't have to run this pixel group by tally because it's going to take some time. That I can show you on my side here. So on my side, 77 images. I think all of them have the same number of observations, meaning that all the ones that were kept, or maybe one of them didn't in the end. But they all have very few NAs, again, because we apply those filters. All right, you can skip this plot on the pixels because that takes some time. Skip the ggSave, but I want to plot here this one. So the one with where we filter only a few pixels and do a time series of them. So make sure you run that. Let's inspect that plot. All right, so look at this. So we have a lot more images. We have some abnormalities here. So this date here, which seems like is 2019 06/14, no, 15. This is 15. It has this very low drop here. And it's kind of has this jigsaw pattern all across, right? So it's not a very clear signal. And very interestingly, like we have a very consistent and consistently low gradient DVI up until maybe like end of June. So I don't know when was the planting date on this field, but you can kind of see that it seems like they planted later, right? Because you only start seeing the crop really increase in vigor after almost July or early July, which is different from what we saw in 2017. So with this, I want to just filter out a couple of dates that had very abnormal values. So one was June 15, which is this date right here. And the other one was in the end where we have this very huge drop as well. You could decide to remove different ones. I think it would be up to you, but I just decided to remove those two because seem to be the most dramatic ones. So if just run that pixels F, we're just removing those dates. Now, again, you can go ahead and run this median chunk. It's just going to show that pattern for one pixel. Yeah.
Can you put this date?
Yeah, I think, oh yeah, sorry. Yeah, that was a difference in the code. That's, yeah, my bad. Yeah, so you're going to have to change these dates here on your side. All right. And then, so making this plot here, we're going to see again the pattern for one pixel, and then we're going to be extracting the median of that pixel, or I guess of all pixels, but this is just an example of how that looks like. So we create the backup again. Here's something else you're going to have to change your date for the backup. I decided to take the first date because that date did have all the observations. So you can just write this down on your side and make sure you run the geometry backup. So you create that. Then after that, if you come to the next chunk, I don't think you have to change anything. We're just extracting the median for all the pixels over time, just like we did before. And then we're just gonna plot it. So you can go ahead and run this chunk here. It's not gonna be a bad chunk, or it's not gonna take a long time to run. So here we see maybe a slightly different pattern. So we see lower gradient DVI on the western side. I'm sorry, on the eastern side. You see that if you remember, this was a lower elevation part of the field. So the pattern of like, at least, looking at this, the way I would interpret is the pattern of crop vigor median of the season is a little bit different from 2017. We can do that DG save and save this figure to file. I think I still have here the yield from 2017, so this does not, it's not the interpolated map for 2019, so you can just ignore for now. I didn't change that part of the code. And then just make sure you export this median of 2019 to file. So just have to run that chunk. You're gonna get the GeoJSON exported to file. All right, so save this script. I want to tell you the following. I want to finish today doing this for all 3 dates. So because Monday is going to be our last meeting, and I want to show you how can we create the stability, spatial temporal stability classes using imagery data instead of yield data, and see how they compare. Again, with the goal of, if you do not have yield monitor data for a field, how well can we still learn from imagery on the different yield potential of the field, just using satellite imagery. So I'm going to go ahead and I will keep going here. Yes.
One of my code wasn't running.
Was that
It's the Pixels F.
Pixels F?
Yeah, I have the dates, but it'll run it if I take the second day out.
Okay, so if you delete this second date, then it works. Is that what you're saying?
Yes, but my code doesn't. I guess it was on the last one. I don't have the as date.
Oh, yes. Okay. Thanks, Doug. I think I remember this. So I think on the 2017, I only removed 1 date. In this case here, we're removing 2. And so we have to have this as date and the C. Yeah, thanks. I guess I forgot that was a difference here. So please do that on your side, and then that should work. So I do want to tell you all that because I want to finish doing this processing for the 2019, we're probably going to go about 10 minutes later. If you have to leave because you have something else going on, you can do it. So that's fine. I'm just going to keep going here, and then you can catch up later with the recording if you need to. All right, so if you run the Pixels F, really make sure that you just export or do the geometry backup, do the pixels median, and then export pixels median for this year. Make sure you do that. All right, so we basically did the processing for 2019. I want to go ahead and do the same thing for 2020. So again, if you just open on your file system, that folder, you go on code. This time around, copy the 2019 completed and paste that, because there are some differences from 2019 that we made already in your 2019 code that you will want to do that for the 2020 as well. So copy the 2019, paste it, rename it to 2020, and then launch that 2020 script. You can close the 2019 script. I would propose that you clean your environment again, just to make sure that you're not going to, because all these objects have the same names. So we don't want to make, want to make sure we're working with only the objects for that year. So if you have the 2020 script now, let's go through it again. You have to bring in the boundary. You can skip the image. You can skip image W. You can skip the map view. On the rest list, we have to change. So this, again, the only difference is I would just delete the whole path and just navigate to the proper folder. So // we go in data, we go in class cotton, all that name, 2020, so that's the folder we want. The pattern is still the same, so then everything should be good from there. If you check the length of rest list, we have 105 images, so not as many as 2019, but more than 2017. The all images. See, we have a comment here for window. Oh yeah, Gonzalo, thanks for the reminder. So in this next chunk, the separator, if you're on Windows, change to set 274 / instead of double / as we already talked about it. After that, you don't have to change anything in this code. You can just run it. We're not gonna print things here, just for sake of time. So if we check the duplicates now, we can run this chunk just to see. We have 29 days that have at least one duplicate. Some of them have 2, 4, 3, and so on. We're gonna apply the same concept of calculating the percent of NAs in the next chunk. So make sure you go ahead and run that. So you can skip all the map views. You can come to the all images F, where we are again applying, keeping the minimum NAs, and if there's 2 duplicates, keeping the least time to be closest to solar noon. And if we have anything that still has more than 50% NAs, we're taking that out. So in the end, we have 58 images that we're gonna keep in this data set out of the 105 initial ones, so almost half. Run the all images crop, so we get the we crop to the field boundary. This should be the same code. We can wait a little moment for that to go through. It went through on my side. We're gonna extract the pixels again. There's nothing to change here, so just run that chunk and let it go through. All right, it went through on my side. We can check the number of pixels. So it's about 2.6 million pixels in this case. Do not run this plot here. It's going to take some time on your side. You can do this after class if you wish. Let's run the pixels when we filter, drop geometry, filter some of them just to look at the growing season pattern. We again see here a sort of a delay initially in the season. So it seems like starts taking off around mid-June. So, sometimes what people have done in the past, which we're not doing in this class here, but people may use these types of data to estimate planting time, right? So you can kind of estimate that after the crop starts taking off, you may take, I don't know, 7, 5, 10 days before it takes off as your planting date. So you can use imagery to estimate planting date and harvest date as well. In this case, we have one image that seems to be abnormally low, and that is July 3rd, I think. So I'm removing that. Please make sure you change these dates on your side. So I'm removing 2 images because of abnormally low values, 2020 0703 and 2020 0810. So make sure you run that. So we remove those images before calculating the median. All right, you can run the next chunk if you wish. It's just to inspect that one pixel and the median for that pixel over time. This is how that looks like. There's still this jigsaw pattern, which could be real. Maybe it could be like, I don't know, water stress that, it's stress one day and you irrigate that day and then the next day it recovers. But it may be just sensor noise as well, especially because, again, this data is not coming from the same satellite every time. It's potentially coming from different satellites. So there could be those discrepancies there. All right, doing the geometry backup, I'm using 2020 0415. You're gonna have to change that date on your side. Then we are creating our pixel median. I don't think there's anything you have to change. Just make sure you round the chunk. Then you can run the next chunk, which is making the plot. Which this year we see this pattern, which I thought was interesting, at least on my side. At least the pattern on the color, right? So this is just the way the color scale is working, is a lot of the field has low median values in my case, because I have a little part on the west side that has very high vigor. And I think that is not even cropland. I think that may be, I don't know, a grassy area or something like that, a grassy way. So, I mean, I guess it is what it is. We could potentially come back in my case and decrease the boundary, make the boundary come closer to the field and not incorporate that. But anyways, I think that's going to be fine as long as this area here appears in every image, meaning that if I use the same boundary for all ears, you know, is that bias, I guess, is going to be equal. It's not like just 2020 had that extra. So you can save this plot. The date that I use for the backup is 2020-04-15. Yep. And then in the end, just make sure you run that last chunk to export this as a GeoJSON. And that wraps it up. I know we flew by these so fast that you're probably not even sure what we're doing. I would recommend that if you want to better understand, go through it again on your side after class, slowly understanding what's going on. But this would be the full scripts to process all three images. Next class is going to be our last class, but we're going to be bringing these median values from 3 years to calculate spatial temporal stability classes, just like we did with yield, but this time with imagery, and see how well they relate to each other. All right, that's all I have for today. Sorry we went a little bit longer. I'm not going to really give you much time to ask anything if you have questions. But if you do have questions, let me know by email. I'll try to get back to you as quickly as possible. And I do want to take your attendance as well. So let me go ahead and do that. All right, so issue is open. Please make sure you make it to the last class, as that's going to be our last meeting time. And yeah, it's going to be important to have you all here attending live. So thank you so much, and I'll see you on Monday.